Hey guys, so these are your flip notes for water and the properties of water. The solutions are going to be on another one. So water is inorganic. That's basically because organic things have carbon in them, and we know water is just H2O, so there's no carbon. It's one of the most important compounds for living things. Again, something you can think about. You know you need water. Think about how you feel when you haven't had water after an hour of physical activity. If you didn't have water for 4 days or any time more than that, you would likely die. And all animals and plants are like this. Water has polar covalent bonds between the hydrogens and the oxygens, and then hydrogen bonds form between the one water molecule and another water molecule. I'm going to explain that in a minute. The structure of water, like we said, it's H2O, so there are two hydrogens and one oxygen, and they're covalently bonded. The uneven distribution of electrons causes a slight polarity of this molecule. So you don't need to know the 105-degree angle. I just want you to see that these lone pairs up here, this extra negative, makes the oxygen region of the water molecule partially negative, and that leaves the hydrogen side partially positive. This is what allows hydrogen bonds to form between water molecules. So if you look here again, the oxygen is partially negative, and this just means partial, and the hydrogen is partially positive. So when we're looking at bonding and the opposite charges attracting each other, the positive end from one water molecule attracts the negative end of another, and this pulls them together, and that's what creates a hydrogen bond. So again, the negative region and the positive region, positive hydrogen, negative oxygen, being pulled together. And because of the polarity and the hydrogen bonds, there are 6 unique properties of water. Water is a universal solvent. It has high surface tension. It can go through capillary action or use capillary action. It's resistant to temperature change, has a high heat of vaporization, and when it freezes, it's less dense than it is in its liquid form. So looking at the solubility of water, because water is polar, it can dissolve other polar substances, so like sugars and ionic substances like sodium chloride, like salt. This is crucial for our bodies to function normally because we need the sodium from sodium chloride, and if water couldn't solvate that and pull the sodium away from the chloride, we would not be able to function. When you're looking at rules for solubility, it's like dissolves like, so because water is polar, it can dissolve other polar substances. It cannot dissolve non-polar substances like oil. So the same way the opposite charges attract each other, the water molecules, if you look in this picture of the beaker, the green here are the chlorines, and the water molecules, the positive hydrogen ends, are attracted to the negative chlorines and pull them apart to solvate, or to dissolve, or to just pull them apart. Water can also has cohesion, which is the attraction between molecules of the same substance. So same as covalent bonds, looking at the two of the same thing. And this is what causes the round drops on the surface of an object. It causes surface tension, and it is a player for causing capillary action. This is essentially what causes water to stay together. Then we have adhesion. Think of adhesive tape. You're adhering two different things together. So this is the attraction between molecules of different substances. So this would be water and the inside of a beaker, or water and a window. Why is this important? This is what causes the meniscus, so that's that dip when you're trying to measure water in a graduated cylinder. And this causes water to hang on to other surfaces until the gravitational force exceeds the adhesive force. All that means is that if you threw water on the wall, it would stay there from adhesion, but as we know, it drips down. That's because the gravity is pulling it down. Surface tension is created by the cohesion of water molecules and the adhesion of water to its container. So the water is holding itself together, and then it's holding itself to that container. So when the surface tension is great, even paper clips can float on the top of water. And that is what allows these bugs over here to walk on water. Now they also have some adaptations in their body style, and that they're really light and they have these tiny feet that they can spread out to distribute their weight. But the surface tension is high enough for these bugs to actually walk on water. Capillary action is one of the forces that draws water out of the roots of plants. If you think about a tree and you know you want to water a tree at the roots, because they have a large network of roots. So even if this is a 100, 200 foot tree, the tree can pull the water from the ground and get it all the way up here. This is because capillary action. And capillary action has a cohesion of water molecules that holds the water together. And over here we have little tubes or columns. If you think about this as like a straw, if you put a straw in water, it will start to climb up the sides. The smaller circumference tube has a higher water level, and that's because the pressure is greater. So you can see that on the bottom here when you're looking at the same size. If you put a straw in water, or a glass straw, the water will start to climb up, and then it actually exceeds the height of the water in the beaker. And this again is from the surface tension, and we have the cohesion of the water molecules together and the adhesion of the water to the glass rising. And this is what allows you to, if you put dye in water and you put a flower or a celery stalk, you can track the dye traveling up, and it will dye the outsides. It won't dye this area in the middle because the capillary action pushes things against the side. Water is also resistant to temperature change, and the only thing I want you to pull from this is think about when you're going to the beach in the summer and it's 90 degrees out and you can't wait to go in the ocean, and you get to the water and it is freezing. Water takes a lot of energy to change temperatures, so it's resistant to temperature change. It also has a high heat of vaporization, so vapor turning into vapor. Think about when you're trying to boil a pot of water to make some pasta, how long it takes in comparison to if you're heating up the sauce. This graph right here, it's showing you how much heat input, and that's a unit of energy because this is measured in calories. How many calories or how much heat or how much energy you need per gram of water to get the water to turn into a vapor. And you can see it's from ice, and then it's going into liquid, and then there's a mixture of liquid and water vapor, and you need 800 calories per gram of water, and this is 100 degrees Celsius to get water to turn into vapor. When water freezes, it's less dense than the liquid form. And this is because we have some hydrogen bonds that are usually breaking. So over here it says liquid water. The hydrogen bonds constantly break and reform. In a solid state, there's a fixed structure, and the hydrogen bonds are stable. If you look at a crystal lattice of ice, it looks very rigid and organized. That's because these are not moving around. These areas in the middle here are open. So these open spaces make water lighter or less dense when it is frozen than when it's liquid. And this is what allows you to fish on top of water and not fall through. But the key thing here is that the water, when it freezes, it stays on the top. If the water froze and this big sheet of ice started sinking, all of the fish and the entire ecosystem of the ocean would be thrown off if this ice then sank and pushed them all down to the bottom. If they weren't able to get out of the way, they would get squished by ice. And this ice also acts as an insulator. It seems kind of crazy that ice would keep you warm, but the temperature of the water very rarely will get lower than 0 degrees. But as we know, in Antarctica, above the ice, the temperature could be negative 20. But under the water, it's, say, 10. So it's still really cold to us, but the animals underneath are more adapted to living to that temperature. So it actually acts as an insulator as well. And again, all of these properties are because water can form hydrogen bonds and because water is polar. Okay, that's everything.